Hi, and welcome to the next instalment of the Oxford Centre for Personalised Medicine Flash Interview Series, where we discuss different aspects of personalised medicine with people involved in the field in one way or another. Today's guest is Dr. Andrew Douglas. Andrew, welcome. Could you start off by telling us a bit more about yourself and your background?
Great. Okay. Well, thanks for having me. I am a clinical geneticist, and I'm currently working in the Oxford Centre for Genomic Medicine as a consultant there. And I also am working part-time in a research capacity with the University of Southampton, attached to Professor Diana Borelli's group, which works mainly looking at splicing in rare disease and how we can use that in a diagnostic capacity to try and find new diagnoses for patients.
Great. So, what does the term personalised medicine mean to you? And how does your work kind of link in with the aims and the objectives of personalised medicine?
Okay, well, I guess personalized medicine is a very commonly used term. It's very much in vogue. And I guess, yes, it could mean different things to different people. When I hear that term, because I've trained, I suppose, in medicine, I immediately think, well, actually, all medicine is supposed to be personalized because everybody sitting in front of you is a different person. So you ought to treat them differently. And hopefully people do that. But I suppose what people are really talking about is how do you actually treat them in a different way with therapies and drugs and things based on some aspect of how their disease manifests or some aspect of their, for example, their genome or their genomic information that could help you either to maybe stratify them into different groups or the ultimate goal would be great if you could actually just take one individual person and make their own medicine that is just for them. And that's a really exciting thing that actually has been done in at least one or two cases. And that's what I feel is truly personalized medicine is, making your own drug just for you. But I guess that's only possible in certain circumstances.
Great. So, what sort of circumstances are we talking about here then?
Well, I suppose when you start looking at genetic diseases, then a lot of them are very rare, and in fact, within each genetic disease, a lot of people, a lot of individuals would actually have their own what we call their private mutation, which only they have, and which nobody else in the world has ever had before. And in some settings, you could actually design a therapy that could actually potentially repair or at least treat that genetic abnormality. And there's different ways you could do that. And one way would be a form of gene therapy, where you could actually potentially go in and try to repair the genetic alteration with a sort of CRISPR-Cas9 gene editing approach. But in many ways, that's quite difficult to achieve in a living person. But the other way is something that I'm interested in, which is looking at the RNA. And the RNA, I guess people listening to this might know about RNA, but in case they don't, then the DNA, which is your instructions manual for your genes, is read and copied into a working copy that is RNA. And that gets processed, and all the sort of bits in between the protein coding regions, the introns are spliced out, and you get your messenger RNA, which is then exported from the nucleus and then gets translated codon by codon into amino acids and make your protein. And because it's outside the nucleus, or at least it's a target that is made and it's sort of turned over, then it presents itself as a drug target. Because DNA is sort of locked away in the nucleus, it's quite hard to get at and to modify in a controlled way. But RNA, because it's being constantly produced, you can actually design drugs that bind to it, recognize it specifically based on its sequence, and then cause the cell to manipulate it and potentially splice it, for example, in a different way that could actually lead to a productive protein again. And that's what is meant, I suppose, by these antisense oligonucleotide therapies that are particularly interesting for me, that can manipulate RNA splicing and processing, and in some cases try to repair something that is damaged.
Brilliant. So I guess then, compared to where we were 10 years ago, how much has the development of these therapies shifted the way that we might be able to treat patients like now and in the future?
Well, let's see, 10 years ago in 2011, I don't think there were any licensed oligonucleotide drugs on the market, except for maybe one that had been designed a couple of decades previously and that had been cancelled. However, since then, we now have a good handful of these antisense drugs that have been licensed around the world. And I guess the biggest blockbuster of those has been this drug nusinersen, which has been developed for spinal muscular atrophy, this sort of previously incurable, untreatable disorder of childhood that was the most common genetic cause of infant death worldwide. And through many, I guess, several decades of working out the molecular pathogenesis of this condition, it was realized that you could actually treat it with a splice modulating drug, an antisense that actually makes use of another gene, in many ways a pseudogene of the SMN1 gene, SMN2, and you can actually manipulate that to create the protein that these children are missing. And actually you have to inject this expensive drug into their spines on a regular basis, but actually it stops them from dying. And in fact, now they're doing clinical trials that show that they're achieving their motor milestones, which they previously couldn't do at all. And probably if you treat them early enough before the symptoms come on, they may have really quite minimal disability. The only downside is you have to treat them with this very expensive drug for life, probably. So that's been a big blockbuster, and I think that's what's been responsible for a lot of the hype in oligonucleotide therapy, which I suppose I should say is not hype, it's reality, and it really works in that case. And that's now been applied to several other diseases, and even has been applied, as I was saying, to some of these individualized medicines. So about 3 or 4 years ago now, there was a little girl in America called Mila, and she had this condition called Batten disease, which is this neurodegenerative disease that causes your central nervous system to slowly degrade, and gives you loss of eyesight and seizures and developmental regression. And she had the standard sort of genetic testing that picked up one mutation in the gene CLN7. But in order to have this disease, it's recessive, and so you should have 2 mutations. So they only found 1. And what happened was they thought, well, someone must be able to find the other one because it's got to be this. So her mother put out a call on Facebook and said, could anyone maybe do some whole genome sequencing to try and find the other mutation for my daughter? And by chance, the wife of this doctor in Boston saw this call and said, oh, I think my husband does that sort of thing. So she, and there was a guy called Timothy Yu in Boston, and he said, oh yeah, we could do whole genome sequencing. They did it, and they found that there in one of her introns in the CLN7 gene, she had this insertion of, I suppose, an abnormal bit of DNA that had just been inserted there, a retrotransposon, and that was causing the gene to be spliced abnormally. Now, because that was a completely new bit of DNA, there was no way you would see that by doing the standard, I suppose, exome type testing, where you just look at the exons that you know about. But by doing a whole genome, you could see it. And what's more, they suddenly realized, oh, this is a splicing abnormality. We could block it and get the cell just to splice over that abnormal thing and repair the protein. So, all credit to them. They pushed for this, and they quickly designed several versions of this drug. And they actually tested it in vitro, and they went to the FDA, the Drug Regulatory Authority, and said, can we do this for this child who otherwise is going to die? And they said, oh, well, okay. So they just had to do one study in rats to show it wasn't very toxic, and then they injected her with this single drug. It's not going to work for anybody else. It's literally an N of 1 study. And she's still, I believe, still on this drug, and her symptoms have settled. And I suppose she will just continue. It's not reversing it, but it's stalled the disease. And that will happen within 1 year. So from the call on Facebook to being injected into her spine intrathecally with the first dose of the approved drug was under a year. And that's because you want to do it as quickly as possible because of the degenerative nature of the disease. So that's a really fantastic example of how you can do this sort of thing if there's the will. And of course, you need the right disease, you need the right sort of people there to do it, but it can be done in some circumstances.
That's incredible. So I guess finally then, if we look forward to the next 10 years, where do you think this field might be going, and what do you think might be the major milestones and the potential challenges of further integration of these kind of personalized therapeutics into the clinic?
Well, that's a really good question, and hopefully it'll all work out really nicely. I think, especially in the UK, in the past few years, there's been a big drive for genomics in terms of diagnostics, and of course that brings with it lots of challenges in terms of interpreting data and variants. But at the same time, which is not so high profile, there has been this big revolution happening in therapeutics, and for some reason, those communities are sort of separate and they've not been very used to talking to each other. And for example, there are gene therapy societies in the UK, but they don't really talk to the genetics communities in the UK. And sometimes I've tried to get them in touch with each other, but it's tricky. And I think there needs to be more integration between those people, because we have, in this country, a lot of expertise and a lot of things happening. And so I hope that in the next 10 years, that integration will happen. And ultimately, with having this rapid access to genomics diagnostics, we hopefully will be able to get to a point where you get a fairly rapid diagnosis. And in some settings, that's going to lead you to find that there's something that could actually be treatable. And if you have this infrastructure set up that then this is highlighted as a potentially treatable condition, then you could potentially develop like an antisense drug for it. And there's lots of hurdles. You've got to get the approvals, but I think that's what we've got to aim for if that's what we want as a society. Obviously, there's lots of cost and time involved, but there are organizations trying to do this around the world in America, and there are companies who are trying to, not at profit, to try and make some of these drugs. I guess it's a good thing to do. And so I hope that's going to work, and I hope that's going to happen. One other thing to say, though, is that this can only work if you understand the diseases. And something that I think has been found by some of these oligonucleotide trials that haven't worked so well as expected has been that there hasn't been as much understanding of the natural history of disease. And as a clinical geneticist, I would say that my community has a really massive role to play in that, because we have all this family data of these super rare diseases, in our departments and coming through our departments. And we could really help all of this if we had an organized way to collect all of that natural history information. Not only would that be useful for our own patients, we could tell them, well, this is what we know about what happens to these diseases, but also we could actually start generating standardized measures that could be used for clinical trials as they come along. So yes, I think the future is really bright, and I hope that we'll be able to be here to witness this transformation in personalized medicine that really needs to happen. And it's just having the right people on board at the right time and the right will, and that requires all this lobbying of the right people and this groundswell. But if you start setting these things up, then there are all these companies out there who want to develop the next sort of wonder drug. And I think if we set up the things like the registries and the information about the natural history, then they'll come and they'll be able to implement these things easily. So
Lovely. Thank you so much. Do you have any final comments before we finish?
No. I mean, thanks for inviting me, and I hope you find lots of other people to talk to and get their opinions. So yeah, feel free to come back at some other time in 10 years and see if I was right, but we'll see.
Brilliant. Thank you.
Thanks very much.